The homework is due on Friday. I think now I've set up Blackboard so that you can upload homework online. So it's due 5 p.m. I think the way Blackboard works, you can still upload it after 5 p.m., but it will show up as late.
Can I take a cell phone picture of my homework and post that?
So I was about to say, yeah. So for cell phone pictures, as long as it's legible enough to grade. So please make sure that it's legible enough to grade for a cell phone picture. For some weeks, I think it will be. For other weeks, maybe it won't be. You can also, you're also welcome to type homework, although for math, that's not usually, that can be a little more challenging. Some of the homeworks are computer homeworks where I guess, you save your computer output and then upload that. So I think now I've set it up for all of the assignments to be able to turn them in online, but I find the Blackboard interface really bad, like it's something from 10 or 20 years ago. So I'm not sure I did it all correctly. And it would be helpful if you actually turned it in online instead of turning it in by hand to the undergraduate office in Clark 113. We'll still accept it at 113, but if you do that, then the graders have to scan it, and I think it's just easier to keep track of it if you turn it online. So I'm not requiring it, but I'm encouraging it. All right, so then the homework, so this is the homework that's due today. So for question 1, I had a question about, for problem 1, whether you have to show your work, essentially, and the answer is no. Unless I say show your work, you don't really have to show your work. And if you have another way of doing it, you're welcome to do something the way that you know how. So, but just remember that for question 1, a guide for quizzes and exams is really the homework questions. So also the quizzes and exams are closed book, closed notes. So you should be able to answer any homework question without using any external resources. So like even if you do the homework using external resources, like that should teach you, you should figure out how to do it without having to look something up. Yeah.
There's no Laplace transform tables on the exams?
Probably no Laplace transform tables on the exams. So for exams, I provide an equation sheet, and I give you the equation sheet before the exam, I think, so that you know the equations that will be provided for you. In previous semesters, I've done things like let students have open book, open notes for some exams, or to let students prepare their own equation sheets. But I found that instead of actually studying, then all the time is spent into writing really, really tiny. So, so no equation sheets on your own. I'll provide one and I'll let you see it ahead of time, I think. All right. So then, yeah. So like, for example, for question 2C, where it says, take this limit, like really then part of the homework is showing when you take the limit, you get the right answer. And there we go. All right, so that's homework 1 due tomorrow. And then I've added the next chapter to the notes. Also, as I go through, I make some changes to previous chapters sometimes. So there's some changes to the previous chapter. Sometimes just typos. Sometimes it's adding material. So one new thing that I decided would be nice to show is that that the sum over, they're sort of highlighted, maybe not. The sum over the eigenfunctions is essentially an identity operator for functions. But again, like don't worry that you've read the notes and then I put something new in the notes and all of a sudden there's something new that you're responsible for and you have to keep looking back over the notes to see if there are any changes. Really what you're responsible for are the homeworks. Okay, so that's that. So I'll exit. All right. online notes. All right, so now any questions before we start? That's too small to matter. It's too small. All right, so so we have one more day of math, and then we go to applications where we use the math we've learned to calculate the response of cells to different perturbations. So where we left off was the response function for a basic signaling element in a cell. The response of a cell at time t to an input at time 0 we calculated as 1 over 2 pi, the integral minus infinity to infinity d omega e to the I omega t over I omega plus alpha. So that's where we left off. This is my pocket. And so this is a formula for a response element where you change from an inactive state to an active state based on an input, and the parameter for the input doesn't show up here because that we provide separately, and then it relaxes back to the inactive state with rate alpha. And because we're integrating with omega, it would be nice if we had omega by itself in the denominator. So we'll just take out the factor of I. So d omega e to the I omega t over omega minus I alpha. Okay, and what we're going to do to evaluate this integral, so we're going to evaluate this integral explicitly. So this will become the inverse Laplace transform type integral that you're used to seeing when we rotate our coordinate system. But because we derived it with omega, we're just going to keep omega here. And so here is the integral. So here's the omega axis. And we're going from minus infinity to infinity. So we'll do that by, instead of going from minus infinity to infinity, we'll go from minus capital U to plus capital U, and then take those n's to go to infinity. And we have one trouble point in this integral where omega equals I alpha. So everywhere else the integrand is well behaved, but when omega equals I alpha, so here is I alpha, then the denominator of the integrand gets really, really, really big. So everywhere else we have a nice convergent power series expansion for the integrand, except right here the integrand blows up. And the way that we're going to do this integral is we're going to add 0 to it in a way that makes the integral 0 easier to do. So the way we're going to add 0 is we're going to think about omega in the complex plane as u plus iv, where u and v are pure real, and omega has a real part and an imaginary part. Our integral then is just, the integral that we're starting with is an integral of the pure real part of omega with the imaginary part 0. And then we're going to add on 3 parts to the integral. So here's the integral we want to calculate. And we're going to add on a step up here. We're going to call it A. And then a step across that we'll call B. And then back down we'll call C. And we're going to show that each of those lines, we can do those integrals and the value is 0. So that if we add this piece plus this piece plus this piece plus this piece, we're making a big loop, but the value is the same as just the integral along the real axis, because we'll prove that this piece is 0 and that piece is 0 and that piece is 0. So here we go. So So this integral, so we'll start with the integral that we want. So the integral we could write as 1 over 2 pi I, and then the integral of d little u from minus capital U to capital U of e to the I ut over u minus I alpha. So along the real axis, the integrand is well behaved. It's just a difficult integral to do, but the integrand is well behaved because u is pure real and never equals I alpha. So we get a value from this integral. This is the response function that we want to calculate. All right, so what we will call A is, so in the notes I just factor out the 1 over 2 pi I. Yes?
How did we prove that b was 0?
We wait 5 minutes.
Oh.
First I'm going to prove that A is 0, then we'll prove that B is 0.
No, b.
V?
The part of omega that's imaginary.
Because that's the integral that we're doing. I mean, so we are indexing our eigenvalues by omega. We haven't proved it's a complete set of states. We're just taking that on faith. But our integral, this integral d omega minus infinity to infinity, we're thinking about omega being real here. What we're saying is we're going to blow our minds and just extend omega into the complex plane. So this integral here, omega is pure real.
It's just given? Yes. So we haven't, so all right. So we started off by saying we have this operator ddt and we're looking for eigenfunctions of this operator ddt. Yeah. Okay? And then we said, oh look, e to the I omega t, where omega is, you know, a real number, is an eigenfunction of that operator. Okay. All right? Now, and then what we're doing is we're saying, all right, let's build functions out of these eigenfunctions e to the I omega t. Right. Okay. Now, what we didn't prove is that that's a complete set of states. Yeah. For example, you know, can we use eigenfunctions of the form e to the I omega t to make, say, exponentials, you know? So we didn't prove that it's a complete set of states because there's only so much that we want to prove. We'll just, you know, assume it's a complete set of states, and we've, you know, we sort of remember that we use Fourier decomposition to, you know, to get things. I mean, really, if there's a non-zero overlap between an exponential and like a cosine wave or a sine wave, then that essentially is the coefficient of the Fourier series. And then, so like, you know, as long as we don't have a function that's completely orthogonal to sines and cosines that isn't itself a sine or cosine, then really we sort of trust it's a complete set of states. So that's, so yeah. Okay.
So in this case, wasn't his question just why is omega equal to u in this equation? And to answer that question, you can just say we're along the real line, so there's no imaginary part, so b is 0.
Yeah. Yeah. Great. And then I thought he was saying, but why isn't there an imaginary part?
Yeah.
So
we're integrating along the real portion in this case. In this case.
Yeah. Yeah.
Okay.
Yeah. Exactly. Exactly.
Okay.
But in another world, it could be like, you know, omega real isn't the complete set of states.
So
that
if you do A and C and B,
yeah,
there will be a B part.
That's right. That's right.
So then my other question is why, so my understanding is we're trying to define that portion along the real line.
We're trying to do that integral along the real line.
We're trying to do that integral. Why do we need A, B, and C?
Because that is because this is a hard integral to do otherwise. Like how would you do this integral otherwise?
I wouldn't.
Like you look it up, so this is like I'm giving old guy stories. When I was a graduate student, we had this big book called Gradstein and Rizek that was a big table of integrals and series and products. And it was big. It was like a doorstop. And now I guess there's Mathematica. But yeah, like you know, because this is the way, for a long time people couldn't do this integral. Like, you know,
300 years ago. People would look at this integral and they wouldn't know how to do it really, other than knowing, well, when you do the forward integral with the Laplace transform, and there's a huge breakthrough in math with complex variables where people figured out how to do integrals like that one.
Okay.
So we are,
I'm just confused how adding a bunch of things that are 0
makes it easier.
is going to make it easier, but let's do it.
We're gonna do it. All right, we're gonna buckle up. So that's what we want. So this is the main piece. That gives us the response function. So this integral A, so I'm going to call this A over 2 pi I, and B over 2 pi I, and C over 2 pi I, just to factor out this 1 over 2 pi I, so I don't have to keep writing it. So then A is equal to the limit as V goes to capital V. So I'm sorry that little v's and capital V's look very much alike, except the capital V is just bigger, unlike U, that the small u is a little weak, so it needs the extra little thing to stand up on its own.
You could add horizontal lines to the tips of the big V.
So then I could make the little v a squiggle, but then it looks like something else, like a nu or a cauldron sign or something. All right. So 0 to infinity dv now of e to the I times capital U times t, e to the minus, well, maybe a little v. So I'll make that a little v. There we go, got a little v. Divided by u plus I times little v minus alpha. All right. So actually, if this is a d omega, there probably should be an I dv. So, but it's going to equal 0 anyway, so that I we won't worry about. All right. So this is what we want to calculate. And actually, what we care about is the magnitude. So we'll put absolute value signs around it. So we want to make sure the magnitude goes to 0. And then the absolute value of an integral is smaller than the integral of the absolute value of the integrand. So the integrand can, the sign can go up and down, and we add up those little ups and downs, they can cancel out. If the integrand is always positive, then the absolute value of the integral is the same as the integral of the absolute value of the integrand. So the absolute value of A is less than or equal to, and we'll just remember we're taking the limit that capital V goes to infinity, so that should be the capital V there. So this is less than or equal to the integral of d little v, the absolute value of e to the I capital UT, and then the absolute value e to the minus VT, so that goes 0 to capital V, of the absolute value of u plus I times v minus alpha. All right, so the absolute value of e to the IUT is 1. That's just, the magnitude. Yes?
Where did we say that capital V goes to infinity?
Right here. So what we're doing is we're just taking a path that, this is a trouble point. We want to get as far away from it as possible. All right? So we want to, make a big loop that captures it. We're going to keep it under control. And then we'll deal with it later. All right? So now, the reason, so we'll see that integrals that are loops are easy to do. All right? So this is why we're doing this. So an integral that's a loop, integrals that are loops are easy to do. In thermodynamics, you learn that, as you are on the loop, if you're in a state function, you come back to where you started. So then most things you integrate around a loop. So we'll get to that. Most things actually are 0 when you integrate them around a loop. So we want to integrate around a loop. And the reason why we're making the loop go this way instead of this way is because we're thinking about positive time. So with positive time, we get a minus sign up here, and a goes to 0. If we were doing this integral for negative time, then closing it in the upper half plane, a wouldn't go to 0. This integral a would be very, very big. So for negative time, we would close on the bottom. Yeah.
You just choose that u is equal to n pi or something?
Excuse me?
In order to get that absolute value equal to 1, you just chose that.
No. So no, that's not why. So the absolute value of a complex number is the square root of the number times its complex conjugate. We're talking about the magnitude. So the complex conjugate is e to the minus iut. They're just saying like cosine squared plus sine squared is 1, so the square root is 1. Okay. So v is pure real. And we're thinking about positive times, so t is pure real and positive. So the absolute value of e to the minus vt is just e to the minus vt. So this thing on the bottom, so think of this as the magnitude of a complex number whose real part is capital U and whose imaginary part is I times v minus alpha. All right? So the magnitude of u plus I times v minus alpha is greater than or equal to the magnitude of mu, of u. So then 1 over this is less than or equal to 1 over the absolute value of u. So here, this here. So that means this is less than or equal to, so less than or equal to, the integral 0 to infinity d little v e to the minus little vt divided by u.
Clarification. So are we doing the magnitude in the numerator? Are we doing that in the integral right there? We have all the magnitudes. Is the magnitude all the way throughout? Because you just mentioned absolute value.
So when I say magnitude, I'm taking that to be the same as absolute value.
Okay, so not like an number.
L1 norm. So wait, say you're about to say something? Yes.
Can you repeat why the e to the negative vt, why that's a negative exponent?
Oh, okay. The reason is we have e to the I omega t, and then we're saying omega is equal to u plus I times v times t. So that's an e to the I ut and then an e to the minus vt. All right. And then this integral we can finally do. So that's 1 over capital U. And the integral dv 0 to infinity e to the minus vt just brings down to 1 over t. So when t is equal to 0, we have some trouble. So often things are not exactly defined when t equals 0. However, for any finite t, in the limit that u goes to infinity, 1 over ut goes to 0. So so truly we need u big enough that for the time t we picked, u times t is still large, so 1 over u times t goes to 0. You'll not be responsible for this proof, by the way. So there are some things that will prove that you will be responsible for, but you should understand how this all works, but you're not responsible for it. All right, so that's integral A, and it turns out, so in the notes I'll go through some of integral C, but integral C, if you write it down and change variables, you'll see it's just the complex conjugate of integral A. They're complex conjugates of each other. So I think you can sort of see that if this line integral is 0, then by symmetry this one should be 0 also. We still have to do integral B though. So, yes?
So why is the limit for a from little v to big V, but then at the very last integrand limit, you go from 0 to infinity?
Because you misread it.
So tell me when I'm warmer. Here? Here?
Yeah, sure.
Oh, yeah, that should be a capital V. Yeah.
So why is there a limit from little v to big V in the beginning? What's the...
Here? From here? Here? Oh, limit, because I screwed up. That's why. Limit as big V goes to infinity.
That's actually what I asked.
You should have pressed me on it.
So does the limit hold through for each of those inequalities, or is it just
Yes, the limit, really I should be writing that here and writing that here. But then you'll see this capital V ends up not really mattering in this one.
Sure, yeah.
Right? it ends up mattering so here it's like, here we're integrating over little v, but it's actually a property of capital U that we're figuring out. And it'll be the same way when we do part B, that we're integrating over little v, but it's big, we're integrating over little u, but it's big V that comes out. All right.
And then is big V in the imaginary plane?
Yes. Yeah, so big V is pure real, but it just tells us how far we're going in the imaginary plane, and we'll imagine like going out to infinity.
I see.
All right. So now we are, so I'm going to erase what we've done with A. So what we've learned is that as long as t is positive, it goes to 0. If t is equal to 0, we have to sort of do something else. All right. So for the response function for a time lag of 0 is sort of the instantaneous response of a system. And really no physical system can really respond instantaneously. So to some extent, it ends up not really mattering for anything physical. It's more a convention we take. So for example, for the unit step function, what's the value of the unit step function exactly at 0? Does the step function go from 0 to 1? Like at 0, so the value at 0 is 1? Or is it like for values less than 0, the value is 0, for values greater than 0, the value is 1, and we should take 1/2 in the middle? So, and in the end, for a lot of problems, it ends up not mattering. So that's sort of what's going on here, that when t is exactly equal to 0, hopefully that never really affects the answer to any physical system. All right, so now we'll get to B. So B is equal to the limit as capital U and capital V both go to infinity of the integral of d little u from big U to minus capital U, because now we're going to the left. So so we're going from the positive side to the negative side. And then du, and then the absolute value of e to the I little ut, e to the minus capital Vt, divided by the u plus I times capital V minus alpha. So we put absolute value signs. And then this is greater than or equal to the limit as u and v go to infinity. So we do the same thing where we move the absolute value signs inside the integral. So when we put the absolute value signs there, that goes to 1. And this is a positive thing that come outside the integral. So we get e to the minus capital Vt, then the integral du, and then with the absolute value signs, we can swap the direction of the integral from u to minus u to instead go from minus u to u to make it look more normal. And then we have a 1 on top because the absolute value of e to the iut, that's going to be less than 1. Or the magnitude is 1. And, I'm sorry, I should have been a less than or equal to. There we go. And then on the bottom, we have the absolute value of v. So when we take the magnitude of the denominator with the absolute value, this complex number is bigger in magnitude than v on its own. The magnitude of I times v is just v. So, so now we can do this integral. So this is equal to 2 times u over v, because u and v are positive. So if we take u and v to go to infinity together, so we tie them together, then u over v, we can set that ratio to 1. So this is less than or equal to 2 e to the minus vt. So again, as long as t is positive, we can choose v big enough to make this part equal to 0.
How about t was defined along the x-axis, no? Of this integral here? I may be mistaken.
So what was what?
It would be equal to u, no? When you take u to infinity, you would also have t as infinity.
So t is the time that we want to calculate the response function at.
So it's held constant over this whole integral.
So t is a parameter. So h of t, this is how we calculate the response function at time t. So t is just a parameter. We're not integrating over t, we're integrating over omega. Yeah.
Two things. In the limit, it's big U and big V.
Yes.
And where does the little u go when you take the magnitude? How does that not?
Oh, so the magnitude of e to the I ut, all right? So like, you know, you could write this as the absolute value of cosine ut plus I times sine of ut, or whatever. So this magnitude is equal to the square root of cosine squared plus sine squared of ut. So that's just 1.
Right. In the denominator, though, where does the little u go?
Oh, in the denominator, it goes away. So this is the same thing, that the magnitude of u plus I times v minus alpha, this magnitude is greater than or equal to just the magnitude of v on its own. So think about this as a vector in the complex plane whose real part is u and whose imaginary part is I times v minus alpha. All right? So here's our complex plane. And let's draw this point. U plus I times v minus alpha. So here we go. This is u plus I times capital V minus alpha. And then the magnitude of v is this. So that's just v on its own, all right? Really IV, but you know, whatever. So what we're saying is this length is bigger than this length, right? So that means that 1 over this, so this length is bigger than this length. So 1 over this length is smaller than 1 over this length. And that's how we keep the less than inequality. Yes?
Does that depend on the values of u and alpha?
No. No, just like think about it in your head that, you know, here is a vector with two. Oh, so what it needs is that alpha is positive. Yes. So it needs that alpha is positive and capital V is positive. Yes. So if alpha were negative, then we could get, could get a different answer. But here, so alpha is positive, and the reason why alpha is positive is alpha is our relaxation rate from the active state. So alpha has physical meaning. Alpha isn't just like, you know, a placeholder variable here. Alpha is, in our physical system, it's the rate that we relax from the active state to the inactive state. So we know alpha has to be positive.
Well, even if it was negative, you get the same answer anyways. The length of the vector can't be smaller than u. So just prove that, and then you have your inequality anyways.
Yeah.
Doesn't matter if it's positive.
Actually, it doesn't matter because v is going to infinity. We just need alpha to be finite, and we do okay. All right. Oh, there's a question in the back.
Why can't you just say, like you did last time, that the bottom, whatever is in the denominator, has to be less than u?
Oh, because here, like, little u can be 0 along this integral. So we're integrating over little u, so we can't really do anything special with it. Capital V is what we have to work with, because that's going to infinity. All right. Yes?
Do you still require the limit of u and v going to infinity at the last part of the inequality?
Well, so we know that u is going to, so u is going into infinity also. We just need them to go to infinity at the same time.
To the negative VT term?
Oh, so that says that v has to go to infinity. It has to be large enough that v times t is still large. So if t is small, if we get t very, very close to 0, as long as it's finite, we can make v big enough that e to the minus vt goes to 0.
What I'm asking is, shouldn't that term also be there in the final term? Like, shouldn't it be limit of u, v to...
Yeah. So so this still should be, you know, the limit as v goes to infinity. There. Yeah. I'm just dropping that because I was lazy. And it's really that, you know, it's the limit that v is big enough so that v times t goes to infinity.
Yeah, another question.
If u was 0 in that denominator expression right there, in the diagram that you just showed, wouldn't that make v less than v minus alpha?
Yeah, so wouldn't that make less I times v minus alpha? V minus alpha. Oh, that's a good point. So what we would get then is we get a term of like alpha over v that then goes to 0. So yeah, so I was a little sloppy. So what you're saying is then the absolute value times v, so we'd have something like absolute value v minus alpha. So this is equal to the absolute value of v times the absolute value of 1 minus alpha over v. And then this we could expand. So if we have 1 over absolute value v minus alpha, what we get is 1 over the absolute value of v, and then 1 plus alpha over v. And then as v goes to infinity, alpha over v goes to 0. So this term ends up not contributing as long as v goes to infinity. So you're right, that's a good point. We're still okay. All right.
Sorry, can you explain that again?
So what he said was, I screwed up here because v minus alpha, it actually doesn't go out as far. It only goes out to here, say. All right? So like then if it's like if alpha is here, v minus alpha is a little bit smaller. So here's the picture. Here's v. Here's v minus alpha. This vector is smaller than that vector. So it seems like we're in trouble, that the proof falls apart. But it turns out we're still okay because we can expand this and we get a contribution like alpha over v, but alpha is finite and v goes to infinity, so we're still okay.
Okay.
Yeah.
So you just skipped a couple steps, simplifying the rest of it?
It's not that I skipped it, I just I screwed up. And then I was fast enough thinking on my feet to show that it wasn't a problem anyway. So it's like a graduate oral exam. All right, and then in the notes I show that C is the complex conjugate of A just with a change of variables. So now we have an integral around a loop. So now I will erase all this. So we're all done with limits. So we have that h of t is the integral around a specific closed loop. Oh, at least let me finish writing this down. I'm sorry. All right, then we'll go back to your question of e to the I omega t over omega minus I alpha. All right, yes?
If alpha over v goes to 0, what about 1 over v?
1 over v also goes to 0.
There's nothing.
No, so we have a 1 over v, but remember we're doing this integral from minus capital U to capital U. So that's, 1 over v is small, but we're doing it over a very long line. So the integral that we got in the end was du from minus capital U to plus capital U of 1 over v. And then we had the e to the minus vt in front. All right? So yeah, 1 over v is small, but we're integrating something small over the entire real axis. So, you know, they have to fight it out. And what we're saying is we'll just let them fight to a draw so that when we integrate this small thing over this infinitely small thing, we're integrating 1 over infinity from minus infinity to infinity. So what happens when you integrate 1 over infinity from minus infinity to infinity? It depends on how things go to infinity, and use L'Hopital's rule to figure out the ratio of infinite to infinite. And because we're in charge of the horizontal and the vertical, we can decide how they go to infinity relative to each other, and we'll just say, let them go to infinity together. So essentially, we're saying capital V, let's just make it the same as capital U as we're taking these things going to infinity. And then the integral of 1 over capital V from minus capital U to plus capital U is 2.
And then, but remember, it's still multiplying the e to the minus capital VT in front. So we get a constant times 0, so that gives us 0. All right. So here we are. All right. So this circle around an integral sign, if you haven't seen it before, it just means you're doing an integral over a closed loop. This isn't enough information to do the integral because someone has to tell you what the closed loop is. So you'll just remember that this is the closed loop that we're doing. Sometimes, people put a C down there for, over a contour, and then you name the contour C, but that still doesn't give you the information unless you can ask C where it's going. So we're going to think about contour integrals. So say that we have a function, since we're using omega, f of omega. So capital F of omega is a function of omega, and it has derivative d omega f omega is equal to little f of omega. All right. And now we're going to do an integral from omega 0 to omega 1 d omega little f of omega. So this is equal to capital F of omega from omega 0 to omega 1. So that's equal to f of omega 1 minus f of omega 0. All right, so that's that should be reasonable. All right, so now we are doing an integral over a closed loop. So now let's not really think so much about the details of where the loop is, but here's omega 0 and there's omega 1. And they're right next to each other. So for most functions, we're sort of coming back to omega 0. For most functions, f of omega 1 is equal to f of omega 0. So that means d omega f of omega equals 0. So that's sort of puzzling that we're coming back to where we start, and if we have an integrable function, if we have a function, where we're taking the derivative of it and then we're integrating that, it seems like we should get 0 for any closed loop of a function where we have where the integrand is the derivative of a function we know. But with these complex numbers, it actually, you can get values. So one example that you're familiar with is just the square root function. So the square root of 1, is that 1 or is it negative 1? And so if we integrate, say that f of omega is equal to the square root of omega. All right. So now this is so inside the derivative we would have the derivative of the square root. So we would 1/2 omega to the minus 1/2. But then we integrate it, we get capital F of omega as omega to the 1/2. And say that we take as our contour something around the complex plane. So we'd start at some value omega 0, and then some value around here is omega 0 e to the I times some angle theta. And then we come back around, we come back to omega 0 e to the 2 pi I. So then the integral around this loop of d omega f of omega, where f of omega is d omega omega to the 1/2, is equal to omega 0 e to the 2 pi I to the 1/2 minus omega 0 to the 1/2. And then just to make it easy, so we get omega 0 square root times e to the pi I minus 1. So e to the pi I is minus 1, so we get minus 2 square root of omega 0. So that just shows you there are a lot of functions where when you come back around to where you start, you pick up a contribution that shows up as a non-zero value to the contour integral. And actually, I think there was like this famous work just recently, well, not so recently, like in the late 80s, early 90s, called Berry's phase, that people figured out some new effect where this happens, where when you go around, you pick up a phase. Did someone say something? No?
Is this the curl of the function?
Is this the curl of the function? I don't think so.
No? And the curl of the vector FW.
So I'm not.
From that, you could also get the flux going through the surface that you just contour on.
So now, I don't know. Now you're blowing me away. So. All right. So for a lot of functions, we get a contribution. Let's see where we are in the notes. So one thing to notice, though, is that there are functions where we never get a contribution. So say that this capital F, of omega is equal to the sum over integers c sub n omega to the n. And here it doesn't, so this is the function after we've integrated it. So say the function after we've integrated it has a series expansion that it just depends on integer values of its argument. In that case, then f of omega 0 has to equal f of omega 0 e to the 2 pi I, because when we take an integer power of e to the 2 pi I, we get 2n pi I, so that always equals 1. So it's only when we integrate something and we don't get integer powers that we're in trouble. So here with the square root, when we integrate something and we get a non-integer power, then we get a contribution. So really, getting a contribution sort of takes the special case that when we integrate the function, all we get is integer powers. But that means that if we have an integer power expression for our integrand, then we can integrate it term by term, and the integral of an integer power gives us an integer power back, and so there's no contribution, except for one very special integer power. So the integer power, if little f is equal to 1 over omega, then when we integrate it, we get log of omega, and then we get a contribution. So now also think about Taylor series expansions. If a function is continuous and bounded in a region, then we know we can write a Taylor series expansion with all the coefficients being finite, and it's just a sum of integer powers where like it's a constant in higher powers. So if a function is well behaved in a region, then when we do one of these loop integrals, we get integer powers back and everything is 0. So it's only places where a function is not well behaved, say in terms of a Taylor series, that we can run into problems. Problems meaning we get a contribution to the integral. So that means that for our integral here, like this is really the only place where the integrand is not well behaved. So you could think about doing a contour where we just like avoid this and make a little cut around it. And then the integral around this loop is 0 because everywhere inside this loop the function's well behaved. And the integral around this loop with a cutout, it's equal to the big loop minus sort of going around this direction with the small loop. And then, and essentially the integral around the big loop collapses to just an integral around the treble point. All right.
Prove that it was 0 though.
We prove what was 0?
That integral there was 0 even with the trouble point inside of it.
No, we didn't prove the integral was 0. We proved that when we add on the pieces, we prove that we could change the line integral to a contour integral that surrounds the trouble point. We didn't prove that the integral is 0. If the integral were 0, that would be a big problem. That would say the system response function is 0. However, if we cut the trouble point out of the contour, like if we take a detour to avoid the trouble point, then we know like in this region the function's well behaved, so the integral around a contour that cuts out the trouble point is 0. So essentially what that lets us do is to think about, it's sort of like a topology thing, that here's the trouble point, here's this big contour we're doing. We can essentially just shrink the contour to the same contour just around the little trouble point.
Is that what we're solving now?
So that is what we're going to do. Yeah. All right. All right. So to see what happens with So we're going to think about a contour of, so here's 1 over omega, where our contour, so 1 over omega has a trouble point when omega equals 0. That's the only trouble point for this function, or pole. So the integral around this contour, 1 over omega, where this distance is omega 0, call it. So we start at omega 0 and we end at omega 0 e to the 2 pi I. So that's equal to the log of omega from omega 0 to omega 0 e to the 2 pi I. So that's equal to the log of omega 0 e to the 2 pi I divided by omega 0. So the log of a minus b is log of a divided by b. The omega zeros cancel, so the radius of this loop doesn't matter. That cancels out. And the log of e to some number is just that number, so we get 2 pi I. So when we take the log of a function, we get the phase. Or when we take the log of a scalar, we get the magnitude plus the complex phase, and then our only contribution to the contour integral is the phase. All right, so now we can finally do our integral. So here we go. All right, so just to make it easier, we're going to change variables to, we're going to say z is equal to omega minus I alpha. So omega is equal to z plus I alpha. So this is integral easy. This is equal to the integral dz over 2 pi I e to the I times z plus I alpha times t divided by z. So that is equal, so remember that, so alpha is a parameter and t is a parameter. We're not integrating over t. So e to the I times alpha times t is an e to the minus alpha t that comes out front. And then a 1 over 2 pi I. So that's just this 1 over 2 pi I. And then this integral dz 1 over z. And now on the top we have an e to the I zt. So e to the I times z times t. And we'll do a power series expansion for e to the I times z times t because we can. So that is equal to the sum from n equals 0 to infinity of 1 over n factorial z times t to the n. So just the Taylor series for an exponential. Oh, there's an I in there. I times z times t to the n. Yeah, so someone about to ask a question? All right, so now all of these integer powers, we can integrate one by one, and when we integrate an integer power around a loop, we come back to where we started and we get 0, except for the integer power here where there are no powers of z, because then there's this 1 over z in the front. So this is equal to 1 plus IZT plus IZT squared over 2 factorial plus higher power. So this is all integer powers. And this is an integer power of 1 over z. So when we multiply this by this, that gives us 1 over z. And we integrate it, we get a log z. And we saw that the integral of log z gives us a 2 pi I. So when we go on a little loop, integral of 1 over z gives us a 2 pi I. And then the next term has no factors of z. So we integrate around a loop, we actually get back to where we started. So that is 0. And here we get an integral of z. So there's a z squared, but the 1 over z makes that a z. But that's an integer power, so there's no contribution to the contour integral. So this ends up, this is the only term that contributes, and we just did that integral. That this is the integral of log z from some value z0 to z0 e to the 2 pi I for coming around the loop. So that's just a 2 pi I. And then that 2 pi I cancels this 2 pi I. So we get e to the minus alpha t is the system response function.
Just a quick question.
Yes. Oh, wait. No, she's first. Sorry.
Can you walk back through that process of simplifying from your summation?
OK. So I'll do that. All right. So this integral is equal to the integral dz times z. And now we'll use the Taylor series for e to the IZT. OK? So or maybe I'll just, dz, I'm sorry, 1 over z e to the IZT. So that's the integral that we're trying to do. For a little loop, like we made the change of variables, so now our contour is a little contour around the origin. So we moved the center of our coordinate system from the origin here to be right on I alpha, because we want to go around the trouble point. OK? So now that's the origin of a coordinate system. We're doing a little contour around there, and the Jacobian of the transformation is 1. So there's nothing special from the change of variables. And now we'll do a Taylor series expansion of the exponential. So we have dz 1 over z, and then an exponential. It's 1 plus IZT plus IZT squared over 2 factorial plus IZT cubed over 3 factorial plus higher order terms. All right? And then we just multiply through by 1 over z. So it's easy to do because they're all integers. So we can do that. So this is equal to the integral dz of 1 over z plus it plus I squared z t squared over 2 factorial plus, so it's like I cubed z squared t cubed over 3 factorial plus everything else. All right? And then we just integrate term by term. All right? So this term, when we integrate it, it gives us a log z that we evaluate at the endpoints of the contour. So log z from z0 to z0 e to the 2 pi I, because this, we're doing it around this contour. All right. Then this next term, we integrate it, we get IZT from z0 to z0 e to the 2 pi I. All right. Now, when we evaluate an integer power of z, so z0 is just z0 back, z0 e to the 2 pi I, 2 pi I, we evaluate it, it's 1, right? So
just bail 0 out.
That just zeroes it out. It's it times z0 e to the 2 pi I minus z0.
Okay.
So it's like you have to put it into the function first before you set e to the 2 pi I to be equal to 1.
Okay.
All right, you have to put it into the function first. So that, I think, for me, that's the confusing part, is remembering that you put it in the function first, and then you can simplify 2 pi I to 1. But you have to keep the 2 pi I there when you put it into the function. And then this next term, like you'll see, that'll give a factor. You integrate z, you get z squared. And then when you put e to the 2 pi I into z squared, that's just, you're squaring 1. That's still 1.
Okay, cool. Thanks.
You're welcome. Okay. So now we have the response function for positive time. So what about negative time? So the issue with negative time is the response function at negative time is the system responding to an input before it's seen it, which would not make physical sense. So for negative time, we can do the same thing for the integral, except then to make it, so here, let me do it on a new picture. So for negative time, so h, so for me to keep it straight, to remind myself it's negative time, I have to say h of negative absolute value of t, rather than just trying to remember that t is negative, because so often time is positive that then I get confused about which direction things are going. All right, so h of negative t is equal to the integral from minus infinity to infinity d omega over 2 pi I e to the minus I omega absolute value of t divided by omega minus I alpha. So it's exactly the same as here, except now we're saying if t is negative, then t is equal to minus the absolute value of t. So just to keep track that we're looking at negative time. All right? And so it's really the same. So here's our real part of omega. And we're doing the same integral over the axis. Here is our imaginary part of omega. Here is our trouble point at I alpha. So here's our integral. But so remember that what we needed is to close the loop. But when we close the loop, we have to add on pieces that go to 0. And remember that one of the things that made it go to 0 is that we had an e to the minus vt, an exponential of minus vt. So when time is negative, we need the imaginary part to be negative also, so we get a negative value. So we have to add on, so we'll call this part a prime, b prime, and c prime. And we could prove the same way that when we add on these parts, that this part is equal to 0, plus this part goes to 0, plus this part goes to 0. So we can say the integral around the closed loop is, we can prove that, we can't just, it's not just we say it, we could prove if we wanted to, but which we won't do because we could use the time more profitably for something else. So, but we could prove that this piece is 0 and this piece is 0 and that piece is 0, and then prove that the integral along the real axis is the same as the integral around the loop. But now, if you look at this function, in this whole lower plane, it's well behaved. So this is just sines and cosines of omega t. And here, alpha is positive, so here's our trouble point. So everything here is well behaved. So the function is finite everywhere here, continuous, differentiable, has a Taylor series expansion if we want to write it, which means that in here we could express this function, say, as a Taylor series in omega that has a constant term plus something times omega plus something times omega squared. So we're not going to prove it, but you could just it's continuous differentiable, it's finite, it has a nice Taylor series, and then just integrate that Taylor series term by term around a closed loop. All of those terms individually go to 0. So what we're saying is this is equal to the contour integral around this contour in the lower half plane, d omega over 2 pi I, e to the minus I omega absolute value of t, omega minus I alpha. And since the pole isn't enclosed by this contour, this is equal to 0. So, we've proved that the response for negative time is equal to 0. Now, it turns out, like, you could actually do this in MATLAB. You know, this is just an integrand, right? So you could set up MATLAB to say, integrate me this function from minus infinity to infinity. So you can do this one in MATLAB. And, you know, it'll try to do it. The problem is that, you know, the integrals that go like 1 over omega, like the integral of 1 over z, that never actually really converges as you make z bigger and bigger and bigger. You get, you know, something that diverges like log. The integral of 1 over z is log of z, which means that MATLAB will go a little crazy trying to, you know, evaluate the integral. And I think it can do a change of variables in the middle. But still, so it ends up converging because of the sign cancellations. But numerically, that becomes very difficult to do. So if you put this into a numerical integration routine, it'll have to work very hard to get something that's close to 0. The integral for positive time it'll do a much better job at, because that converges more easily. All right, other questions? Yes?
I have a question about the diagram. In this case, is that point, that trouble point, the I alpha, is that outside of our...
Yeah, that's outside of the contour, because alpha is positive. Okay. So here, like you can see, when omega is equal to I alpha, you get a 0 in the denominator. Bad things happen with 0, or interesting things happen with zeros in the denominator. So, but that happens outside the contour.
Right, but so how is A, like A, whatever you want to call it, the opposite of A there in the other direction, is that not the same height as A anymore?
Oh, it is the same height. Like it goes, well, instead of going from 0 to capital V, it goes from 0 to negative capital V.
Oh, I understand. Okay. Okay, now I get it. Thanks.
Yes?
Why didn't we do the same thing? Why did we have to have A in the first diagram going up in the like, why couldn't we just go down and...
Why can't it go down? Because if it went down, then we'd have e to the plus capital VT. And then that doesn't go to 0, that goes to infinity. So it's more that the time is telling us whether to close in the upper half plane or lower half plane. It's not our choice. We have to do that for those pieces to go to 0. So, So in the notes, then we just show that
bad point isn't in the contour. That just means there's no response function there.
That's right. Well, what that means is that integral gives 0, so the response function is 0. So the notes has standard things that you already know. I think about Laplace transforms, so it proves convolution theorem. But there's something that you might not be used to seeing that is also in the homework. So I'll do that as the last thing, which is e to the a ddt of f of t. So usually you're used to seeing the time derivative in front of a function. You're not used to seeing it as part of an exponential. So what does it mean to put an operator into an exponential? So what it means is sort of like you can just unwind that by writing the Taylor series expansion for the exponential. So how operators and exponentials are defined is just we do a Taylor series expansion of the exponential. So we have 1 plus a d dt plus a squared over 2 factorial ddt plus a cubed over 3 factorial d squared ddt cubed, all in front of f of t. And then, like, each of these, we know what they do. But then if you look at it, this is just the definition of the Taylor series expansion for f of t plus a. So that is something that you're not, like, I'm not sure whether you're used to seeing things like that. But then sort of something interesting is then, say that we want to do the Laplace transform of e to the a ddt f of t. So this is equal to the Laplace transform of f of t plus a. And then you're used to doing the change of variables to show that this is equal to e to the s times a times the Laplace transform of f of t. So that the time derivative operator in the time domain ends up in the Laplace domain looking like s. And that's because these values of s are the eigenfunctions of the, or the eigenvalues of the basis set that we're using. All right, so that is it for today.